So we're going to move on to chapter 2. And in chapter 2, we're going to talk about the exponential function, logarithm functions, also the application of the exponential function. So let's get started. We're going to take a look at exponential function first. So the exponential function look like this. The typical model look like n to the x. Here n is what we call the base. X is what we call exponent. And the important thing is the base must be greater than 0. So this is foundation for the exponential function, and in this section we're going to learn how to use the properties of the exponents to simplify the exponential expressions. And we're going to learn how to solve the exponential equations. We're going to also take a look at how to sketch the graph of the exponential functions. So, first of all, let's look at some of the basic elements in the exponential function. So in chapter 1, we learned a linear function. So linear function, this first function we learned is f of x, mx plus b. And a polynomial function. So this linear function actually is a first degree polynomial function, because the exponent for the x is 1. And also we have a polynomial function third degree, right? Which is f of x equal to x cubed. So this is a polynomial function. And an exponential function typically has basic form of a base raised to exponent. Base is usually a number raised to x, and this number must be greater than 0. Okay. An exponential function has a variable in the exponent, not in the base. So the variable is in the exponent. That's where the exponential function comes from. And the general form of exponential function, as I mentioned, is f of x equal to n to the x raised to x power. N must be greater than 0, and that's basic structure of the exponential function. And we're going to take a look at some of the properties of the exponents. And you probably learned this in the algebra course, in the intermediate algebra course back in high school. So first one is when we have multiplied two exponents with the same base, a are the same, right? Same base. You just basically add exponent, so it becomes a raised to x plus y. When you raise the exponent to another exponent, then you multiply the exponent x times y. So the result becomes a raised to xy. And if you have two numbers inside of the parentheses raised to x power, you can distribute the power to x, like distribute the power x to a, distribute the power x to b. The ax times b to the x. Now, if let's say we have a quotient a over b, parentheses to the x power, similarly, we distribute power to the a, the numerator, and distribute power to the denominator. So you get a to the x over b to the x. And if you divide into exponent, keep the base, same base, keep it, and subtract the exponent. So it becomes x minus y. And if let's say we have an exponent, the base a raised to negative exponent, then we could turn into 1 over, make it a fraction. And you can flip this exponent to the denominator, make it a positive exponent, and it becomes 1 over a to x. And if you have 1 over a to negative x, then you flip this to the top, now it becomes a to the x, right? And by default, denominator is 1, so anything by 1 remain as is, so it's a to the x. And also we have a raised to x over y, then you can just turn into radicals. So now it's the power goes inside of the radical, and then the y becomes index of the radical. Let me give you a quick example on this. So for example, let's say we have a to the 2/3 power, right? So it becomes cubic root of a squared. And you can also move the power outside, so it becomes QE root of a, the second power. That's what this rule is about. And that's actually how we convert an exponent into the radicals. It's quite useful in a lot of algebra operations. All right, so now let's apply the properties to simplify some of the operations. First one, 2 to the second times 2 to the third. So two exponents with the same base. So keep the base, adding the exponent. 2 plus 3, that gives us 2 to the fifth. 2 to the fifth indicates 2 times 2 times 2 times 2 times 2. We multiply 2 5 times. And that becomes 32. And secondly, when we have the two exponents with the same base again, keep the base, and you add in exponent 2 plus negative 6. So 2 plus negative 6 is 2 minus 6. So it becomes 2 to negative 4. And then we apply the other property. So it becomes 1 over 2 to the 4th power. 2 to the 4th is 16. It's 1 over 16. Now we have an exponent raised to another exponent. Keep the base, multiply to exponent 3 times 2 gives us 6. So it's 2 to the 6. 2 to the 6 means we multiply 2 6 times. And that becomes 4 times 4 times 4. That's 16 times 4. That's 64. All right, so now let's take a look at some more application of the properties. So right here, we have 2/3 raised to negative third power. So one way we can do this is, in order to get rid of this negative sign, then we use a reciprocal of the fraction here. So 3 over 2 to the third power. Now distribute the power to the top. So it becomes 3 to the third over 2 to the third. 3 to the third is 27. 2 to the third is 8. So it's 27 over 8. And similarly, we have 3 to the 7 over 3 to the 9. So same base, keep the base, subtract the power, become 3 raised to the negative second power. Now flip the denominator, make it a fraction, flip the denominator, it becomes 1 over 3 to the second, so it's 1 over 9. Okay. Now so now when the exponents are the same, we can also keep the exponent, multiply the base. So 2 times 8, the same power, half. 2 times 8 is 16. 16 to the half, that becomes, and we turn this exponent into radical, so it's the square root of 16 to the first. So it's the square root of 16, that becomes 4. And another way of looking at this is we can also do this 2 to the half. So turn 8 as 2 to the third to the half. Now we're going to get 2 to the half times 2 to the, multiply this, 3 over 2. Now simplify, same base, keep the base, adding half, and then 3 over 2 times 4 over 2, which is 2 to the second, which is 4. All right. So as you can see, two different approach, same result. Now let's look at how we solve the exponential equations. Let's say we have 5 to the x equal to 125. Now, first step, we're gonna carry over 5 to the x, and we know 125 is 5 times 5 times 5. So 5 to the x equal to 5 to the third. So turn into exponent, get 5 to the third. Now same base, then the exponent must be the same. X must be equal to 3. So you can say we have a to the x equal to a to the y, same base, and the exponent x must be equal to y. Now another example, same base 7, exponent must be the same, so x minus 1 equal negative half. Now from here, adding 1 from both sides of the equation, we solve for the x. Cancel the 1, x equal to 1 minus half is half. Now more equations here. Now a to the x equal to 2. And we know 8, not the same base, right? But we can turn into the same base. A equal to 2 to the third. X equal to 2, right? So now simplify left hand side, multiply 3 and x, you get 3x. On the right is 2 to the first. Now they have the same base. So 3x equal to 1. Exponent must be the same. And dividing 3 from both sides of the equation, x equal to 1/3. Okay. Another example, a to the x equal to 4. Similarly, we already simplified this. So 8 is equal to 2 to the 3x. And then we know 4 equal to 2 to the second. So again, we turn it to the same base. Now the exponent must be the same. 3x equal to 2. Dividing 3 from both sides of the equation, x equal to 2/3. Now more equations. Here 1/3. We get 1/3 to the x, right? And if you on the right hand side, we can easily turn 27 as 3 times 3 times 3. So it's 1/3 to the x on the left, and 3 to the cube on the right. So we're going to turn the 1/3 as a reciprocal 3. That means the power becomes opposite. So now both left hand side, right hand side have the same base. And we get negative x equal to 3. Same exponent must be the same. And dividing -1 from both sides of the equation, x equal to 3. And similarly here on the right hand side, so now the variable is on the denominator, so we're going to apply the multiplication rule of the exponent. Raise the left hand side to the third power, raise the right hand side to the third power. So 1/3 times 3 becomes actually, they are reciprocal, becomes 1. On the right is 27 to the third, and x equal to 27 to the third power. If you expand it, 27 to the third power is 19,683. Okay. Now another example here is x to the raised to 3/4 power equal to 8. Similarly, we're going to raise to the reciprocal power, so meaning raised to 4 to the third power on both sides of the equation. So we apply the same operation on both sides of the equation, and these two reciprocal cancel each other, so we get x to the first, it's 8. 4/3, and then 8 4/3 we can turn it as, okay, some window just pop up, someone have deleted. Okay. So x equal to a to the 4th power, and then turn into cubic root. And now we can simplify this. We get cubic root of a cubed times 8. That's 3 into a cubed, and then a to the first. And now a cubed cubic root becomes 8. So split it as cubic root of a cubed and cubic root of 8. Cubic root of 8 is 2. 8 times 2, that's 16. So the answer is x equal to 16. A little bit of a radicals operation is also, we can review that. So now let's take a look at exponential functions and how we come up with this graph here. General form of exponential function, f of x equal to n to the x. Base must be greater than 0. Now it's like a function notation, so we plug in an x value, we expect to get a y value. For example, so for g of 3, then x value becomes 3, so we get 2 cubed, which is 2 times 2 times 2. That gives us 8. G of 2 is 2 to the second. So now again, this number goes into the function and becomes exponent. So 2 times 2 gives us 4. G of 1. Similarly, it will be 2 to the first. So that gives us 2. G of 0 is 2 to the 0 power. So any number to 0 power is 1. g to the first, g to the negative first, so it becomes 2 to the negative first power, so it becomes 1 over 2 to the first. So it's half. Now g to the negative second is 2 raised to the negative second power, so it becomes 1 over 2 to the second. It's a quarter. And also, okay, so we basically get some order pairs from the function itself. So similarly here, g of 2, right, is 2 to the second, that's 4. So that's why we get 4 here. G to the first, picking x value equal to 1, and we get 2 to the first, that's 2. 2. G of 0, that's 2 to the 0 power, that's equal to 1. G to negative first is 2 raised to negative first power, so it's half. And the last one, g of negative 2, 2 to negative second power, that's a quarter. And so basically we get 5 order pairs, and we can sketch the graph. So first order pair is 2, 4. Second order 1, 2, 0, 1, negative 1, and half. And if you observe the y value here, looks like it becomes half, right? So it becomes half of the previous number. Okay, so we get a 1 and a half, and then negative 2 and quarter. So right here, we're just plotting all these order pairs and get a graph. So make sure you include all these numbers. So the minimum y value is quarter, maximum is 4. On the y value is 2, 3, 4. That should be enough. Get that. And then on the horizontal axis, we have negative 2, 1, and then 1, 2 on the right. Let's start sketching this graph. So 2, 4, that's here. And we have a 1, 2, 1, 2 goes here. 0, 1 goes here. And then negative 1 half is here. Negative 1 half goes here. And the last one is negative 2 and a quarter. Now we're connecting those 5 order pairs, connecting them, extending both directions. As you can see, when the base is greater than 1, meaning n greater than 1, then you can easily see that from the right hand, from left to right, the graph is increasing. Right? From left to right, first one is increasing. Secondly, pass through the y-intercept 0, 1. This is also very special. 0, 1 is y-intercept. And then also, third point is, this curve never touches x-axis. So we have horizontal asymptote. Asymptote is the line, this function getting infinitely close, but never goes through that. So x-axis is asymptote. So by sketching the graph, we'll be able to come up with some observations and understanding the characteristics of the graph, exponential function. And this is a more sophisticated graph. You can easily get it on a calculator. You can also get it in a lot of online graph sketching platforms. Okay, so now next one is this. All right, so similarly, for the exponential function h of x equals 3 to the x. So right here we will get what is h of 2 first, which is 3 to the second power. So 3 times 3, that's 9. and h of 1, 3 to the first, that's 3. H of 0, which is 3 to the 0 power, so that becomes 1. And then at h to the negative 1, and this is 3 raised to the negative first power, it becomes 1 over 3 to the first is 1/3. And then h of negative 2, and 3 raised to the negative second power, get the 1 over 3 to the second, it becomes 1 over 9. Okay, so we get 5 order pairs. So first order pair is 2, 9, second order pair is 1, 3, third order pair is 0, 1. As you can see, it passes through the y-intercept 0, 1 again. Negative 1 and 1/3. And the last one is 2 and 1 over 9. So now we can easily sketch the graph again on the side. So now the y value maximum is 9, minimum is 1, 9. So we're going to need maximum is 1, 2, 3, 4, 5, 6. The horizontal axis, we have 2 units. 1, 1, 2. And again, 2, 9 goes first. 2, 9, that's highest point. Set 1, 3 goes here. 0, 1 goes here. 1 and 1/3. 1, 1/3 is approximately here. Negative 1, 1/3 goes here. And negative 2, 1, 9. I use a different color here. Alright, so now we get 5 order pairs, connect them, extend in both directions, get a graph. So again, the base is greater than 1. And we see the similar graph from left to right increasing. Secondly, pass through the y-intercept 0, 1. Third one is x-axis horizontal asymptote. Same feature as the previous one. Because the base is greater than 1, so the graph looks similar. And this is more sophisticated graph. Try to draw yourself. Now, I combine two graphs together, g of x equal 2 to the x and h of x equal 3 to the x. And we come up with this exponential function with positive base greater than 1. Have a graph that are increasing, right? From left to right, it's increasing, it's going upward. Secondly, the function never crosses the x-axis. So this is x-axis, and we call this x-axis the horizontal asymptote. And also the axis is the left horizontal asymptote. And the smaller base means the graph rises more gradually. The bigger base means the graph rises more quickly. Right? So the base, when the base becomes larger, it's increasing at a much faster pace. Exponential function will not have negative base. So remember, we define exponential function n must be greater than 0, no negative number as a base. Now, we're going to take a look at the natural number e. Number e is called natural number. It's also called Euler number. And e is approximately equal to 2.718 28169. And anything with a continuous compounding nature, we're going to use the exponential function of the base e. For example, in real life, the population is compounding continuously. Also the national debt, right? Treasury bonds, those are compounded continuously. So we can model those using the exponential function with base e. But let's take a look at how the mathematician Euler developed the natural number or discovered natural number in the past. So right here, using this limit for x approaches 0 for x values, and he was able to discover the approximate value of the Euler number or natural number. And you can try in the calculator or the Excel, see how this number getting when this x approaches 0 on both directions, then this result approaches the Euler number, so which is approximately equal to 2.718. Okay. And then it was discovered by the Swiss mathematician and physicist. His name is Leonhard Euler. Right? So that's why it's called Euler number. And it's also called natural number. And the graph of the e to the x look like this, and you can also easily get this graph, f of x, e to the x. And again, we're gonna come up with a t-table x, f of x. So when -2, -1, 0, 1, 2, right? And then when put into the increasing order, so f of -2 becomes e raised to -2nd power. Let me show you what that looks like. E to the -2nd is 1 over e squared. I'm going to show you how to get this in the Excel. So this is equal to e to the second e plus t second and second. It turned out to be 0.114 approximately. If you run it to 2 decimal place, it's approximately equal to 0.14. So now let's go back. So this is equal to 0.14. So this is 0.14. So after -1, that will be e to -1st power. Let's see what that is. It's 1 over e. You can also find it from the Excel. exp to -1st. And this turned out to be 0.37 if you run it to 2 decimal place. Okay. 0.37. And then f of 0, that's e to the 0, which is 1. 0, 1. Again, it passes through 0, 1 because base is greater than 0. Greater than 1. Yeah. Now, f of 1, it's e to the 1st, so it's approximately 2.72. Okay, 2.72. And f of 2 is e to the 2nd power. And again, I'm going to use Excel to show you the result. E to the 2nd. So this is 7.39. Okay. So 7.30. Now once you plot those 5 points, right? So let's say 2, 7.9 here, and 1 is 2.72. That's somewhere here. Once you sketch all those 5.01s here, -1 is 0.37 here, and -2 is 0.14. connect 5 points, we came up with the e to the x. And you see why this is very crucial in section 2.3 when we talk about the application of this exponential function with AC. And then let's say the basis is between 0 and 1. So right here, let's say we do j of 2. So replacing x with 2, so it's half to the second power. So it's half times half is quarter. That's 0.25. Okay, you get a quarter here. J of 1, it's half to the first, it's half, which is 0.5. And then j of 0, again, half to the 0 power becomes 1. And then j of 1 adds half to the first, becomes half. No, half to negative first. Okay. And that becomes, we're going to flip the denominator. So it becomes reciprocal that denominator, right? So it becomes 2 over 1 to the first power. So it's 2 to the first, that's 2. And then j of negative 2, x value becomes negative 2, half to negative 2. Similarly, flip the fraction, it becomes 2 over 1 to the second. 2 to the second, that's 4. Now we get 5 order pairs, and you can sketch it. You're going to see a slightly different graph. So again, the y values here, the minimum is 0, what maximum is 4, 1, 2, 3, 4. Y-axis 2, 1, 0, 1, 2. Okay, let's sketch the graph. So 2 and a quarter, 2 and a quarter goes this is half. Quarter is here, so 2 and a quarter goes here, 1 and a half goes here. Then we have 0, 1, negative 1, 2, and negative 2, 4. Again, it's a 5 points we are using here. So connect those 5 points, extending in both directions. So come up with this graph here. As you can see, we can see some features is from left to right is decreasing. Secondly, pass through the y-intercept 0, 1. Third one is x-axis the horizontal axis. So here the base is greater than 0, less than 1. So between 0 and 1, the graph is decreasing graph. Okay. So quite different. Right? So decreasing from left to right, passing through 0, 1 as y-intercept, and also x-axis is the horizontal asymptote. When the base is less than 1, then graph is decreasing. So why do we study exponential function? Because exponential function used in real life measure growth, interest, decay. So very famous application of this growth based on exponential functions, exponential growth. So that like rumors, human populations. In section 2.3, we're going to take a look at how we model the human population growth using the exponential model of base E. Bacteria, the growth of bacteria, computer technology, nuclear chain reactions, and compound interest. Also could be modeled using exponential function. And decay also obeys exponential functions. So a lot of application in physics, like carbon-14 datings, half-life of those nuclear elements, Newton's law of cooling for exponential decay model. And again, we're going to study the exponential growth model in detail when we reach the section 2.3. That's pretty much everything.